So dear Diu, thank you very much for coming and give a seminar at Ecodep seminar. And so I am very happy to hear about your work and the techniques related to this to those Luxembourg-based methods. So thank you very much. I leave you the word.
Okay. Yes. Yes. So first of all, I would like to thank you for giving me opportunities to give a talk today. So today we are going to discuss about the statistical inference for Vasicek-type model driven by Hermite processes. So this is joint work with Professor Yvonne Tan from the University of Luxembourg. And for my knowledge, this is the first step to estimate unknown parameters of a stochastic differential equations driven by the so-called Hermite processes. So what are Hermite processes? Why we consider the model of a stochastic differential equation driven by Hermite processes? And what are statistical inference problems we would like to investigate in this model? Let us discover the questions step by step. So first, I would like to mention the well-known center and non-center limit theorem, which born the fractional prime motion and Hermite processes. Secondly, for those of you who haven't heard about fractional prime motion, I will mention quickly about definition and important properties of fractional prime motion, so that you could have you could have a background and understand more when we extend fractional prime motion to the family of a self-similar stochastic process, the so-called Hermite processes. Hermite processes, just keep in mind from the beginning, it's a family of stochastic process. They are self-similarities, exhibit long-range dependence, and because these properties we will give you they have an important application in modeling because it's general line of fractional prime motion. So in this section, we focus on the explicit representations of Hermite processes, their properties, and the nice properties of Wiener intervals with respect to these processes. Finally, we focus on our main model, the Vasicek-type model driven by Hermite processes. We give the motivation why we consider this model driven by the extensions of fractional prime motion noise, like why we consider this model driven by Hermite noise. And we assume that in this model, we have several unknown parameters, say grid parameters, and then how we construct the estimator for those unknown parameters. And finally, we study the fluctuation of our estimator around the true values of the estimate of the parameters. Okay, so now we are in the position of our general framework. If we have a stationary Gaussian sequence with mean equal to 0 and variance equal to 1, we denote here rho is a covariant kernel of this stationary Gaussian sequence. We assume that we have a function g is a square interval function with respect to Gaussian measure. Satisfy this condition, this means expectation of a g of a standard Gaussian random variable is equal to 0. In the space of square interval function with respect to standard Gaussian measure, the function g can be expressed in terms of infinite series of linear combination of the Hermite polynomials. So the Hermite polynomial, for example, Hermite polynomials of the one, h1 of x equal to x, h2 of x equal to x squared minus 1, h3 of x equal to x power 3 minus 3x. Because of such condition, so our time series, start from Q, and Q here is always bigger or equal than 1, so that AQ different from zeros. Such kind of Q in these expansions is called the Hermite rank in the expansion of the function G. The interesting questions, the question we are interested in here is to study the limit behavior of such partial sum of a functional of correlated stationary Gaussian sequence. Why we interested in this behavior? Because if you consider example like when G is a Hermite polynomial or other one, and then we have here is the partial sum of xi. So it links you to remember the classical central limit theorem. If G here is a Hermite polynomial of order 2, that means it's equal to xi squared minus 1. 1 here is a variance of xi. So we have the partial sum of xi squared minus expectation of xi squared. So this is this link you to the limit behavior of quadratic variations of a stationary degree of Gaussian sequence. And so on for H3. That's why and such limit behavior could give us to understand the approximation of the stochastic process, to approximate the data, and to construct confidence interval and so on in statistics. The result we have quite interesting. So here, if our stationary Gaussian sequence has a short range dependence, this means the series of its covariance, absolute value of its covariance, power q is finite. So in this case, we have for all order of Hermite rank q bigger or equal than 1, we always obtain the central limit theorem. That means our limit is a Gaussian random variables, Gaussian process. And especially notice here, our normalization term is a square root. This is 1/2. So we have 1 over square root of n. So our power normalization term here is 1/2. In contrast with central limit theorem, so in the case of short range dependence, we always obtain central limit theorem. But if our sequences have a long range dependence in the sense that the series of absolute value of covariance functions are paracute divergent. In particular, we consider its covariance structure given by this function. It's equal to n power 2 h0 minus 2 multiplied by a slowly varying function for some h0 belong to this interval. In this case, we have that the normalization of partial sum of a functional correlated Gaussian sequence which exhibits long-range dependence convert to the family of stochastic process, the so-called Hermite processes. Notice here that our normalization term is the 1 over n power h here. H is bigger than 1/2. h is bigger than 1/2. Later you will see clearly h bigger than 1/2 than now, because h have connection with h0. So h bigger than 1/2 is no longer equal to 1/2 like in the Gaussian, like in the case of short-range dependence. So, and notice here, this is the family of stochastic process of all the q. It depends on q and depend on h. So when q equal to 1, we obtain a central limit theorem, and our limit behavior is exactly fractional Brownian motion. So this gives you a picture about the difference between the limit behavior of short-range dependence and long-range dependence of a stochastic sequence of Gaussian random variables. So this is an example that fractional prime motion and Hermite process were born. So what are fractional prime motion? And what are Hermite processes? We will go for further details now. So don't worry if you don't know anything about fractional prime motions. I will try to present everything in this talk so that you could have the idea about this model and the stochastic process. So for fractional prime motion, so a fractional prime motion, we denote here by the notation p power h. So a fractional prime motion of host parameter, or later we could say of a cell-similar parameter h, is a center continuous Gaussian process with the covariant function given by this quantity. With the host parameter is considered belong to the interval 0 and 1. Especially, notice that when h equal to 1/2, when we replace h equal to 1/2 here, and then it's easy to prove that when h equal to 1/2, we have, this is the classical Brownian motion by proving because both are Gaussian process, so it's easy to check it the same mean and the same covariance. When h equal to 1, then our process fractional prime motion is just a linear function according to t multiplied by a fixed random variable. So it's trivial to consider. So from now, when we mention fractional prime motion, we always assume that h belongs to the interval 0 and 1, not include 1 because of such a relationship. So it's, when h equal to 1, it's trivial and we don't study this. So the fractional prime motion is a popular model for both short-range dependence and long-range dependence phenomena in various fields, for instance, in physics, in biology, hydrology, and finance mathematics. There is many references devoted to fractional prime motions, and one of them I recommend here is the books of Diu Tan, written in 2012, named Selected Aspect of Fractional Prime Motion. Okay, fractional prime motion have some interesting and important properties that make us to model long-range dependence and short-range dependent for phenomena. For instance, it has properties like self-similarity properties in the sense that if you zoom in the fractional prime motions, and then the distribution of fractional prime motion is still the fractional prime motion. They also have stationary increment. That means the incremental behavior of fractional prime motions at any point in the future is the same. When h bigger than 1/2, the fractional prime motion also exhibits long-range dependence in this sense. And it's on the sample path of fractional prime motions also have the order continuous on every compact set. Especially, fractional parameter is not semi-martingale, not macro process, except Brownian motion. That's why the theory of semi-martingale and properties of macro process do not hold when we work with fractional Brownian motion. So we need more further tools and different tools to deal with fractional Brownian motion. Fractional Brownian motion also can be represented explicitly in form of a voluntary process. That means it could be written in the intervals with respect to classical prime motions of the explicit kernel. The kernel here is given explicitly, and it is square interval kernel. And here is for simulation of sample path of fractional prime motion. And here I give you some example of the path of fractional prime motion for different values of Hertz parameters. When we notice here, when you see, when Hertz parameters close to zeros and the sample path more broadly, it's not smooth, then h close to 1. The sample path of fractional parameter when h close to 1, it look smoother than when h close to zeros. Okay, and now we are moved to a generalization of Hermite processes, a generalization of fractional prime motion, the so-called Hermite processes. So in this, I will focus on the explicit representation of Hermite process, some properties so that you could know why Hermite process is an extension of fractional prime motion. For further details and technical and some syntactic aspect related to Hermite processes, I recommend you in the book. I recommend you two books written by B.B. Rust and Taku in 2017, like Long-Range Dependence and Cell Similarities. And the other book is written by Tudor in 2013, Analysis of Variations for Cell-Similar Processes. Okay, so recall that from the beginning. So from the beginning, we already know that Hermite process appear in a non-central limit theorem wrote by Taku, Dobrosin, and Major in 1975 and 1979. So you already know that the limit behavior of such a normalization of path to sum of a fractional correlated Gaussian sequence convert to the Hermite processes. And in the limit behavior, you see here the relationship between H and S0s. So S0 is some S0s is appear in the covariant structure, which make this sequence become to have a long range memory, or long range dependence, long memory are the same. So because our limit behavior depend on is a family of stochastic process depending parameterized by the order Q's and the Hertz parameter H. So notice here when for all order Q bigger or equal than 1, our Hertz parameters H always belong to the interval 1/2 and 1. That's why when we construct when we give the exhibit representation of Hermite process and when we give definition of Hermite process, we always have that Hermite process defined for Q bigger or equal than 1 and Hertz parameters belong to 1/2 and 1. When Q equal to 1, this is a fractional prime motion. this is the only Gaussian process in this family can have the Hertz parameter defined in the interval from zeros and one. Okay. Actually, a Hermite process can be represented explicitly as a multiple Wiener intervals. So before moving to give you an explicit representation of Hermite process, we are now to quickly recall what's the multiple Wiener intervals. So if we have a Brownian field defined on a property space satisfying the expectation of two different Gaussian field, Brownian motion field, or more general Gaussian field, it's equal to the inner products in the space of square interval function of their kernels, and then the Q will, and then we define a closed linear space of L2 omega generated by the family of random variable like Hermite polynomial HQ of the Brownian field. When its kernel is a square interval function with norm is equal to 1. And such kind of family of random variables equal Q with the chaos, because it's generated by the Hermite polynomial or the Q of Brownian field. So by using such kind of mapping we can extend it to the linear isometries between the symmetric square interval function and the Q winner chaos. After this extension, we could define the multiple winner intervals for any square interval function f. And in notation, we denote such kind of random variables is like this. And we may write the multiple winner intervals in this form. So if f symmetric, we could you could understand this is the iterated stochastic intervals. I highlight two important properties of multiple winner intervals: the orthogonality, isometry, and hypercontractivity properties. The orthogonality isometry properties telling us that the expectation of two different multiple winner intervals of different orders is equal to zeros if it's the same order and it equal to the inner products in the space of square interval function of their kernels. And here we assume that f is and g, their kernel is symmetric square interval function. So if f and g are not symmetric, and here we could have some symmetrization of the function f and the function g here, and up to a constant here. So for hypercontractivity, so this kind of inequality telling us that all L carry norm are equivalent for any case bigger or equal than 2. For further detail about the multiple winner intervals, about more detail about construction step by step and other properties of these intervals, I would recommend you to look at in detail in the book written by David Nuala in 2006, The Malia Rank Calculus and Related Topics. And in this book, you could see more general picture about the construction of multiple winner intervals. Okay, and here I give you the explicit representation of Hermite process. So a Hermite process of order Q bigger or equal than 1 and a Hertz parameter H belong to 1/2 and 1 can be viewed as a multiple winner ether intervals. The kernel here, the kernel in this representation here form up as intervals of such special function. The constant B here is two-side standard prime motion, and the constant here is calculated to be sure that the variance of a Hermite process evaluated at time 1 equal to 1. And H0 here, depending on H is equal to 1 plus H minus 1 divided by Q. So why H0 equal to this quantity? You look at again our story where Hermite process come from. Yeah. You don't need to remember this kernel. Okay, so if Hermite process of order Q equal to 1, and we have the fractional prime motion, this is the only process in this family of Hermite process to be Gaussian and could define and only process defined for self-similar parameters as in the interval 0 and 1. When the Hermite process evaluated at time 1 is called Hermite random variables, and any random variables which have the same distributions are Hermite process evaluated at time 1, also called Hermite random variables. Especially when Hermite process of order Q equal to 2, they have special name. This is called the Gaussian-Plus process. Are denoted in the torque. The Gaussian-Plus process denoted by R power H here. And similarly, a random variable will have the same distributions as Gaussian-Plus process evaluated at time 1 equal Gaussian-Plus random variables. So Hermite process share a lot of properties with fractional prime motion. Example like cell similarity properties, stationary increment. They even share also the same covariant structure. You look at here, they have said the same. They also exhibit long-range dependence when h bigger than 1/2. So it's the same with fractional prime motion. They also have Holder continuity properties with the same order. And furthermore, they also have finite moment. When we do finite moments, we use hypercontractibility properties to get this result. So except Gaussianity, so as soon as the order of Hermite process Q bigger or equal than 1, bigger or equal than 2, they are no longer Gaussians, only fractional prime motion corresponding to Q, the order Q equal to 1 is a Gaussian process in this family of this self-similarity stochastic process. Because they share many properties with fractional prime motion, so this makes a Hermite process become potential good candidate for modeling, and it's also good candidate when our data is not exhibit the Gaussianity properties. But unfortunately, the explicit distribution of Gaussian-Plus random variable as well as Hermite random variable when the except fractional prime motion is not known so far. Only numerical approximation are available, And then we see here a mysterious conjecture given by Taku and Wet in 2013. As I know, so until now they haven't solved it in mathematics, in mathematical proof. So we see that the CDF of a Gaussian black distribution intersect at two different points, according to different value of Hertz parameters. One idea to prove it is we consider CDF of the Gaussian black distribution as a function of Hertz parameter h, and then we could use technical of fixed point technical to prove that it converges and have to fixed point when the Hertz parameter is changing. Okay, and finally, we don't forget to mention for any type of stochastic process, we are interested in the problem for the integrals with respect to this stochastic. So for the stochastic integrals with respect to Hermite process, is well defined for any deterministic function f satisfying this interval condition. For construction of such kind of integrals, we start when f is an elementary function, and then we use the definition of a Hermite process. Later, we will extend it in this space, and then we have by using Cauchy criterion, and then we have the conversion. This is the sense for construction of integral with respect to Hermite process. So they also have isometry properties in the sense that the expectation of two different stochastic integrals with respect to Hermite process is given by this quantity. And interesting and important that the Wiener integrals with respect to Hermite process can be expressed as a multiple Wiener Ito integrals. Even by this form, the constant here is the same in the definition of Hermite process, and this term are also the same. So the Brownian motion here is a two-side classical Brownian motion. Because notice that it's the same, because when we choose when we take the function f here, is an indicator function like this. And then when we replace this indicator function in this kernel, and then we recover the Wiener integrals with respect to Hermite process of this indicator function, we recover is exactly Hermite process. So it's the way for easier to remember the representation of Hermite process and the integral with respect to Hermite process.
I'm sorry to interrupt you. What is H0?
Yeah, S0 is S0 is the constant appear in the definition of Hermite process here.
Okay.
Yeah, and why is S0 have such kind of form? It come from the story of where Hermite process come from.
Okay,
This
sorry.
one, yeah. When they study special center stationary Gaussian sequence with this special covariant function.
Okay, sorry.
Yeah.
Thank you.
So feel free to stop me if you have any comment or questions. Okay, and now we are on the position of our main problem, the Vasicek-type model driven by Hermite processes. So So as you already know, like the standard Vasicek model was proposed and studied by Vasicek in 1977 for the purpose of interest rate modeling. The generalization of this standard Vasicek model by replacing prime motion, classical prime motion, by the fractional prime motion. So this extension helps us to model processes with long-range dependence in finance, in hydrology, in turbulence by using a lot of powerful tools of Gaussian analysis to deal with it. So such kind of equations equal the fractional Vasicek model. And A and B here are called RIP parameters. And sigma is here the volatilities of the model. When B equal to zeros, we have the is equal fractional Austin-Uhlenbeck process. The fractional Vasicek model and as well as the special case fractional Austin-Uhlenbeck process receive a lot of attention because its potential for modeling purpose in 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 finance, in hydrology, in turbulence with some phenomenon exhibits long range dependence and short range dependence as well. And because they already have the powerful toolbox of Gaussian analysis to deal with it, including prime motions and also the toolbox when dealing with fractional prime motion and stochastic differential equation driven by fractional prime motion. However, in some situations, for instance, in hydrology, when we analyze river flow time series, when our empirical data attest to presence of self-similarities and long memory without the Gaussian properties. So the lack of Gaussianity and somehow the unknown explicit expression of the probability density may arise us exciting challenges which motivate us to consider an extensions, a non-Gaussian extension of our models, where we replace the fractional prime motion, the Gaussian noise, by the Hermite process. So this equation is called Hermite equal Vasicek-type model driven by Hermite process. So this model, this Vasicek-type model driven by Hermite process have explicit solution given by this term. So remember here it includes two terms. The first term is deterministic term, and the second term form of a stochastic intervals with respect to Hermite process, and the kernel here is an exponential function. When we choose Q equal to 1, of course, we have the corresponding fractional Vasicek model. This is the Vasicek-type model driven by fractional prime motion. And when B equal to zeros here, and then we get the Austin-Uhlenbeck process driven by Hermite process. The problem we are looking at in this model is that we assume that we know Hertz parameters. We know the volatility term with a lot of generality. We assume here sigma equal to 1, and we assume that we don't know the RIP parameters A and B. So the problem we looking at is to construct the estimator for a known RIP parameter A and B. Later, we will study their asymptotic properties, for instance, study their consistency, whether it's converged to our estimator or not, study their fluctuation around the true values of the parameters. We assume here we could we assume here we could observe the sample path of X based on continuous time observation in continuous time. And by studying this problem, we could answer the questions like, do our estimators have the same asymptotic behavior for both Gaussian case and non-Gaussian case or not? So if we remove Gaussian's assumption, we don't have Gaussian phenomenon here, and our data exhibit non-Gaussian case. So the error estimator matter when we changing the Gaussian filter in the model, in the Vasicek model or not. Okay, so the estimator we introduce here is not a maximum likelihood estimator, not least square estimator. So it depending on the mean and quadratic mean of the sample path. Why and how we find this estimator? How did we find it as the estimator? So the way we find the estimator relies on the limit behavior of the mean and quadratic mean of sample path. So we have the mean of sample path convert almost fully to the read parameter b, and the quadratic mean of sample path convert to the square of read parameter b and the function depending on read parameter a, like this. And we prove that for any order q and any Hertz parameter h, that means for any type of a Vasicek model driven by any type of a stochastic process in the family, in the Hermite families, we always have the strong consistency of our estimators. That means it converts to our estimator is convert to the read parameters in the sense that almost surely conversion. Okay, to give you a key when we drew about a strong consistent of our estimator. So recall that the solution of the Vasicek model driven by Hermite process is written in two terms. The first term is deterministic term, and the second term is a stochastic interval with respect to Hermite process of the explicit kernel is an exponential function. So I denote the second term here by white. We write the mean of sample x is equal to this quantity. The first term, by using Lebesgue-Dominic conversion, we prove that it converts to the read parameter p. So it's left to prove that the stochastic term tends to zeros. So we did it by using the properties of multiple winner Ito intervals, because you see here the stochastic interval with respect to Hermite process can be represented by a multiple winner Ito intervals, and then we could use hypercontractivity properties to study it, and then compile to prove almost fully conversion. We use the Boring-Cantelli lemma to obtain to get the desired conversion. So it's the second term tends to zeros. So that's why we easily to prove that the means of sample path x tend to the read parameters b. So for the quadratic mean, similarly, we've written it in three different terms. The first term is easy to check that it converts to b squared. And the second term, we check that it converts to zeros by studying limit behavior of this quantity. So it converts in distribution to the Hermite random variables. So, and then to get the almost fully conversion, we use Boring-Cantelli lemma to get the almost fully conversion. And for the last term, this is interesting term. This is the quadratic mean of the second term of our solution, y here. So recall that. Look at it again. Y here from of stochastic integrals with respect to Hermite process, and the kernel is the exponential function t minus u here. So to study this quadratic mean of the second term in our solution, so first we will observe that the expectation, this quantity. So if we take the expectation of y t square here and take the integral and take the means of that term, and it's converted to this quantity. So to get this conversion, to get the conversion here with no expectation here, we will study the quadratic functional of a long memory moving average process, E like this. So when we study the quadratic functional of the long memory moving average process Y here, and then we get the following conversion difference. We see here in the Gaussian case, that means when Q equal to 1, in case of fractional prime motion, we have in K equal to 1 here, it appear here 1, 2, and 3. So we have either non-center limit theorem because it converts to Gaussian blast, or center limit theorem will arise in the Gaussian case. That means in the fractional prime motion case. But for Q bigger or equal than 2, that means in the non-Gaussian case, Hermite process in no exhibit Gaussian properties. And then we already have a non-center limit theorem. And look at here, the normalization term is also different according to different cases. So using this term, and then from this limit behavior, we compile this one, and then we get that this term will convert to this term will, and then we get that this term convert to this quantity in sense of distribution. To prove that in sense of almost surely, we will again use the Boring-Cantelli lemma to prove it. Actually, the limit behavior of quadratic functional of such long memory moving average process Y can be proved, and often the same result when we generalized by the kernel given by this term and satisfy the interval condition. Okay, now we move to the last one. We study the fluctuation of our estimator around its true values. So in non-Gaussian case, I mean, in the model of Vasicek model, when driven by Hermite process, in a non-Gaussian case, that means when any order Q bigger or equal than 2, and for any Hertz parameter, in this case, we have for any Hertz parameters, we always often non-center limit theorem. Our joy conversion here, depending the limit behavior, depending of the Gaussian block distribution in the first term, and the second term is the Hermite random variables. This is Hermite process evaluated at time 1, and the normalization term given by this one we see here and here. And we have a conversion in distribution. So why we find G infinity here and how it connection with the second term, how it's related to second term, we will see later in the next 2 slides. I will explain more detail about why we obtain the Gaussian block distribution here. Okay, but in the Gaussian case, that means in our model, Vasicek model, driven by fractional prime motion, and depending, in this case, Q equal to 1. So depending on the different value of Hertz parameters, we have either center or non-center limit theorem. So when h less than 3/4 or equal 3/4, And then we have central limit theorem. Our limit behavior is a Gaussian vectors. So n's and n bright here are independent Gaussian random variables. And we look at here, we have a different term of a different normalization term in two cases. Yeah. But when h bigger than 3/4, we have non-central limit theorem. So our normalized terms is also different. And in the limit behavior, it contains the Gaussian blast distribution here and the square of fractional prime motion evaluated at time 1. And then second term, it contains fractional prime motion evaluated at time 1. Okay, in order to study the fluctuation of our estimator and to understand more about why a Gaussian blast distribution, why we have G infinity here, and how it's related to the second term in our Joy conversion, it depends on this kind of this is the key proof of fluctuation. It depends on the following proposition. In this proposition, we introduce another stochastic process denoted by U capital T of T here. So it forms a stochastic integral with respect to Hermite process, and the kernel here also exponential function T minus U, but we have here the capital T in front of. So we study the quadratic functional of this stochastic process, and then its conversion in L2 omega to the Gaussian blast distribution up to a constant, up to an explicit constant. Okay, and I will explain how we use this result to get the Joy conversion of our estimator. So the first term, for the fluctuation of our estimator of the real parameter B, and then we get after normalization T power 1 minus h, we could express, I don't give detail about the calculation here. I just give the end of the result. So it could equal to the Hermite process at the time capital T. And for the second term, fluctuation of the term of estimator H, and then after normalized term, we could and using the Taylor expression, and then we could have this kind of form. In this form, it contained the quadratic functional of the second term of our solution. Why here? And you remember that we already have the limit behavior of this term. Okay, for the fluctuation of Joy conversion, so here we will see that's why our new stochastic process appear, because the term A capital T here appear in our expression of the difference of our estimator and its true values. The AT here is the same distribution of the random variable GT that we introduce here up to a constant like this. So, and using the L2 conversion of this GT, and then we get the limit behavior is a Gaussian blast distribution here. So from L2 conversion, we obtain like conversion in distribution. And as for the Joy conversion, in the Gaussian case, that means when Q equal to 1 and Hertz parameter less than 1/2, bigger than 1/2 and less than 3/4, we use the powerful toolbox of Gaussian analysis to study it. So for conclusion, so do our estimator for A and B have the same asymptotic behavior in both Gaussians and non-Gaussian case or not? So the answer is we already see we have strong consistency of our estimator. the strong consistency is universal for any type of Vasicek model driven by Hermite processes, no matter is it Gaussian or not. But the fluctuation of our estimators around the true values of the read parameters depending heavily on the order queues and the Hertz parameters of the Hermite processes. So this give us to understand how much the Gaussian assumption in the fractional prime motion in the fractional Vasicek model relies on the Gaussian filter. And but one thing I noticed here, I forget to notice, when we look at our estimator here, it only depends on the mean and quadratic mean of sample path of X, and we could observe it. So it's easy because they have such kind of form, so it's easy for numerical approximation. So thank you very much for your attention. So feel free to ask me or have some comments.
So thank you very much, Diu. Yes, indeed, if there are questions or comments, it would be nice to hear. Maybe I have a small question, which is related to the fact that maybe the process is not observed everywhere. Maybe there are discretized versions of this result.
Yeah, these interesting questions. Yeah, I also think that we could solve this problem in case of discrete observation, and also assume that we can, and also study when we don't know the volatility parameters. Example, wait. Yeah, example in our model like this, we could consider our discrete model, and we could consider when we assume that H are unknown and volatility parameter are unknown as well.
And else?
For estimate unknown volatility parameters, we could study the quadratic variations of X.
Yes.
Because it not depend on A and B, and later we will, after know volatility parameters, and then we could consider H, and then we could consider unknown read parameters.
Okay. And up to what I understood, there is no really use of the Maillard calculus techniques in this work.
Yeah, it appear in the roof. Yes.
Okay.
Actually the Maillard calculus appear hidden here, because we in the roof I only use the properties of multiple Wiener-Ito intervals, and have some already have available properties of such multiple Wiener-Ito intervals divided from Maillard calculus.
Okay.
Yeah, that's why I didn't mention Maillard calculus here.
Okay.
To keep the talk more general pictures and simple.
Okay. Thank you. Thank you very much. So I thank you. We thank you again, and we stop recording maybe.